ready.
We can start? Okay. Thank you, Julian. Good morning and good evening for everybody. It's a place for me to announce the CAR 2022, this very friendly conference between Poland and Mexico for many, many years now. So I will be very fast. I just like to say thank you very much to our invited speakers. Thank you very much to all the participants. Thanks very much to the rest of the organizing committee. And follow us in all our social networks, Facebook, YouTube, and in Zoom. So see you later. Thank you, and we can start.
So is it my turn now? Or someone from
my turn
Polish
now
organizers?
or the intro? Okay, my turn, yes?
Yes,
Wait a second, I'm gonna put the video so that we can start.
Okay. It's a great pleasure for me to introduce our first invited speaker, Professor Pawel Pilarczyk from Gdańsk University of Technology from Poland. And he combines mathematical background in dynamical systems and algebraic topology with skills in algorithm design and programming into the development of computational methods for automated analysis of dynamical systems. Today, Professor Pawel Pilarczyk is going to present a talk about graph algorithms at the service of computational dynamics. Thank you for this introduction. Our invitation.
Yes. I'm sorry, do you want to say something more?
No, thank you. We are waiting for your talk now. Thank you. Thanks.
Okay. Thank you. So let me share the screen with the slides. Okay. So I hope you can see the title page now.
Yes, we can.
Yes, everything is now.
We can hear you.
So I'm going to talk about a little bit of my research that I've been doing for already over 20 years. And this is research in a topic that is really far apart from combinatorics. However, I use a lot of graph algorithms. I didn't even expect I used those algorithms were so crucial for obtaining these results. So I'm going to show actually three specific lines of research or three different applications of graph algorithms in the theory of dynamical systems. In fact, this is more practice than theory because we do computer-assisted proofs and we analyze some specific applied dynamical systems. In the first part of my talk, I'm going to show how we use weighted directed graphs for the computation of uniform expansion in one-dimensional maps. In the second part, I plan to explain sort of a new theoretical approach to the perception of dynamics of some features of dynamics at finite resolution, where we also use graph algorithms intensively. And in the third part, I'm going to say a few words about maybe the biggest project I participate in. This is about developing some automated method for analysis of a multidimensional dynamical system. Since this is talk about dynamical systems, let me begin with the definition of a dynamical system. We have a topological space. For example, this is the Euclidean space in most applications. And we have some topological group for measuring the time. This is usually the integers. If we have a discrete time, if we analyze a population of trees and we note the state of the population every year, then we measure the time by integers. Or this could be real time. For example, if we have some process like a chemical reaction that runs along, and we measure, we want to describe the system at each moment in time. In general, a dynamical system on some space X, so we have this topological space, is a mapping. We take a point from the space, we take a time, and then this mapping says where the point goes after this specific time. In order for this to have some reasonable meaning, we need to say that there are at least these two conditions satisfied. If we move by time 0, this means we don't move at all, and that's natural. If no time elapses, then the point doesn't move anywhere in the space. And also, if a point moves by some time, and then the resulting point moves by some other time, then it will be equivalent to saying that the initial point moved by the sum of these times. This means that the system doesn't have sort of memory, and the next position, the next state of the system doesn't really depend on the history of the system, but only on the current state. The discrete time dynamical system usually comes from a map, a continuous map, and we just take iterates of the map. This map in many applications is not invertible, so we cannot have a full topological group. We just take a semi-group, and then we can use forward time mapping only. A continuous time dynamical system usually comes from solving an ordinary differential equation or a system of equations in Rn. And then the trajectories of each point correspond to solutions of the system of ODEs. So let's begin with the first part, where we use weighted graphs in one-dimensional dynamics. Let's take an example, a very famous example of a map. This is the quadratic map. I call it a quadratic map family because there is a parameter of the map, and depending on the parameter, the map may have very different properties. For a equal to 2, the graph of the map is very simple. It's like a parabola upside down, and you see that there is a critical point at 0 where the derivative of the map is 0. If you iterate some points, which is the image of one is, for example, somewhere here, then the image of the next point is somewhere else, we get trajectories. And we look what happens to these points when we iterate them. And in some cases, for example, for a equal to 0.5, after a few iterates, those points get close to a fixed point, which is like 0.25, and all the dynamics stabilizes at this fixed point. When we increase the parameter, then the fixed point is no longer stable, but there is a period to attracting orbit, which means that if we start at any arbitrary point in the domain of the map, after a couple of iterates, the trajectory starts iterating around this period to orbit. For some other parameters, however, there is no such nice behavior of the orbits. For example, for a equal to 2, if you start at any point, then the trajectory doesn't seem to stabilize anywhere. it seems to go back and forth through the entire phase space. And this instability is due to strong expansion in the space. And if you look at the graph of the map, there is some region where the derivative is large and the phase space is bounded. So we get stretching and then folding back into the space. Where we have the critical point, then the derivative is 0, so there we don't have this expansion. And this causes some trouble. We don't want to analyze the dynamics close to the critical point. So I just showed the behavior of trajectories for 3 different parameters. What mathematicians draw is a bifurcation diagram. And here we take the full range of parameters from 0 to 2. And then for each parameter, we plot this attractor in the phase space, a fixed point or a period to orbit, or then there's a period doubling, and we have a period 4 orbit and some other trajectories. For some parameters, you see that there's an entire large interval in the phase space that is sort of grayed out. This means that a typical trajectory just wanders here and there, and it does not stabilize at any specific fixed point or in a specific place in the space. There are some periodic windows, like a period 3 window for some parameters, where again we have stabilization of these trajectories. And the purpose of this project I'm talking about is to get a mathematical rigorous method for bounding this expansion in the space, so that we can prove for which parameters there's at least a chance for chaotic dynamics, and for which parameters the dynamics is sort of stable. So what we want to estimate is the Lyapunov exponent. We start at some fixed point, some specific point in the phase space, and then we iterate this point. And we look how the expansion accumulates along the trajectory by looking at the derivatives. So we take the nth derivative of the function at the point, and then we would like to have this growth in the derivative explained in terms of exponential growth. So we compute the exponent of the growth, which means that we take the logarithm of the derivative and we take the average of these derivatives along the trajectory. So if we take the nth iterate, we would expect, for example, if the derivative is 2 everywhere, then we would have the exponent of expansion equal to 2. So this means that all the phase space is stretched by the coefficient of 2. And in fact, in the ergodic theory of dynamical systems, the positive Lyapunov exponent indicates that there is chaotic dynamics. So it is really a good thing to have a rigorously proved lower bound for this exponent. And if we take just one term in this limits inferior for some fixed n, we can use the chain rule to see that in order to bound this average logarithm, we just need to look at a trajectory of a point, and we take the derivative of the function at the consecutive points. So we take iterates of the point and we just look at the derivative of the function. We don't need to compute the derivative of the composed function or the iterates of the function. So the idea for computing a rigorous lower estimate for the expansion rate is first to find bounds for the logarithm of the derivative in the entire domain of the map. And then we need to trace the trajectories. If I get a little backwards, you'll see that in some regions of the phase space, the derivative is larger than 1 in absolute value. In some others, the map gets sort of flat. So the derivative is very small, at least in terms of the logarithm. So we would like to have a mathematical method, computational method that would trace the trajectories and check that indeed, in spite of those flat areas of the map, the derivative along the trajectories really grows. And here is a statement that we would like to prove. If we take some neighborhood of this critical point, we exclude this neighborhood from the computations because there's no hope in getting positive expansion where the derivative is 0. This would damage all the accumulated derivative growth in the map. And then we would like to have some constants, c and lambda, positive, such that for every point for which its trajectory doesn't drop into this bad neighborhood of the critical point, we indeed have an exponential growth in the derivative. So this derivative in absolute value is bounded from below by the constant, the positive constant c, times e to the power lambda n. And in order to get a method that would compute such a lower bound explicitly, we use directed graphs. Let me briefly recall the definition of a directed graph. A directed graph consists of vertices, directed edges, which are just pairs of vertices, and there is a weight function that we associate with the edges, and this weight function will correspond to the exponent in the growth of the derivative. We split the entire domain of the map into small intervals. Well, this method applies to not only to the quadratic map. There could be maps that have several critical points. So we take these critical points, C1, C2, C3, with some radius of a neighborhood. We exclude this neighborhood of the critical points from the computations, and everywhere else in the phase space we have these intervals, and we represent the map together with the derivative by means of a directed graph in the following way. Each little interval will be a vertex in a graph. Each edge will correspond to a mapping. If one interval is mapped by this continuous map to some other interval, or at least intersects at least some small part of that interval, then we add this edge to the graph, and the weight of the graph will be a lower bound, some rigorously computed lower bound for the derivative on this part of the interval that is mapped to the other interval. So in this way, we construct a directed graph with weights of edges. And now each trajectory in the system corresponds to some path in the graph. This graph is sort of an outer bound for all possible trajectories in the system. That means if we have a trajectory in the system, that for sure there will be a corresponding path in the graph. There might be, however, some spurious paths, but we don't worry about them. We only use these paths to get a lower bound for the exponential growth of the derivative. So here, if we take a path in the graph, the path gamma, that corresponds to some orbit in the dynamical system, then the sum of the logarithms of the derivatives along the orbit is bounded from below by the weight of the path. The weight of the path is just the sum of the weights of the edges, of the directed edges on the path. And in this way, but just by computing a lower bound for the weights of all the paths that we can encounter in the graph, we get a rigorous lower bound for the expansion exponent in the dynamical system. And specifically, there might be some paths that go in loops in the graph. So we look at all the possible cycles in the graph, And here we take the average weight. So the minimum mean weight over all cycles in the graph will provide a number that will be a lower bound for this exponent, for this Lyapunov exponent lambda. And then we have some other paths that don't necessarily go in loops, but they also can run through some areas in the space where the derivative might be low. So we also need to compute an estimate or a specific rigorous estimate for these graphs. And in this way, we get this constant C for our theorem. And indeed, we were able to do some reasonable computations. In order to compute this mean weight for any cycle in the graph, we use Karp's algorithm. It appears in some textbooks for discrete analysis or graph algorithms. And the time complexity is not very bad. It's polynomial. It's like the maximum of the number of vertices times the number of edges, or the square of the number of vertices. In fact, since our graph corresponds to a mapping, the image of each interval intersects only a few, just 2 or 3, typically other intervals. So the number of edges is of the same order as the number of vertices. And this means that the time complexity of this algorithm is essentially quadratic. Space complexity, the original algorithm requires to store a lot of lengths of paths of weights of paths of certain lengths, but it's possible to improve this complexity to linear. In order to get the estimate for the constant C, we use Floyd-Warshall algorithm or Johnson's algorithm that computes the minimum weight of any path between any pair of vertices. These are very classical algorithms. When I was studying computer science, I didn't expect that so basic algorithms will be so useful in the theory of dynamical systems or in ergodic theory. And indeed they are, and the space complexity is linear, the time complexity is V, the number of vertices squared times log V, or so essentially it's quadratic. It's not so bad. And the computations that we did for the quadratic map, here are the results. I restricted the interval of parameters to 1.7 to 2, where we have some periodic windows and some windows where sort of chaotic dynamics can be observed. And here the bound for the Lyapunov exponent that we computed consists with the pictures, what we see in the bifurcation diagram. Whenever we have a periodic window, we have a negative Lyapunov exponent. This means that there is contraction in the dynamics towards the periodic orbit. And for many parameters, we were able to prove rigorously, mathematically, that there is this sort of strong expansion in some small, outside of some small neighborhood of the critical point. So we took the neighborhood of radius 0.01, which is really nothing in comparison to the phase space from -2 to 2. And here we used 5,000 vertices in the graph, which means we split the domain of the map, the domain to the interval. This would be the domain on the bifurcation diagram to 5,000 intervals. We published several papers on this research, the quadratic map, the ergodic theory. This is something that a lot of people work, and there was interest in these algorithms too. Now let's switch to the second topic, and this is about the perception of chaotic dynamics or some dynamical features at finite resolution. The motivation for this research is in some dynamical systems we observe attractors of weird shape, like this is the famous Henon attractor. if you start with an arbitrary point in the phase space, you iterate it forward, you will see that this point runs along some folding shape in the space, and it runs along this shape in a very unordered and unpredictable way. So this is an example of a chaotic system. And in fact, certain properties in chaotic systems, in dynamical systems, concern infinitesimal scale. One proves that for an arbitrarily small neighborhood of some points, there exists some features that can only be seen at very fine resolutions or at arbitrarily small resolutions. But in practice, this doesn't really make sense. In practice, we only have in some real applications, we have some bounded finite resolution of measuring devices. We model some systems with some errors in the model. So there's also some noise in the actual system. So looking at finite resolution is really everything that we really need for applications. This is sort of a philosophical statement. Some pure mathematicians will object, but for practical purposes, I think if we have some property that we can prove at some finite resolution, let's say at some very fine but still finite resolution, that would be equally good for the reasoning about, for example, an epidemiological model that has a statement about any arbitrary resolution. Okay, so this is the motivation, and the practical approach is we take a phase space, for example, a bounded box in the plane, which I show here. We take balls or disks so that we cover this entire space with these disks. We take open disks. In general, we just take open sets, and this is a finite open cover of the phase space. The phase space could be a bounded metric space. It usually is a subset of the Euclidean space, Rn. And we only consider these covers for which there is some area that is essentially covered by those elements. Well, in this theory, there are several assumptions that might not be that obvious, but I'm not going to discuss all of them. Let me go straight to the graphs. So we would like to model some mapping on this space that is covered by this collection of open sets. And we use the notion of a multivalued map. A multivalued map is sort of a map that maps a single element of the cover into a collection or a set of elements in this cover. And we use this multivalued map to represent a continuous map of interest in such a way that the actual image of this ball or this open set that is plotted, that I plot here in this sort of blue or violet color, is covered by the elements of the open cover. So whenever we compute the actual image of some open set, we need to capture all those elements of the cover that intersect this image. And in this way, we define a representation of the map. Of course, we can only do the computations with bounded precision. So we use interval arithmetic to get an outer bound for the image. So sometimes we can get some extra elements in this set. So not always we are able to compute the minimal representation, but nevertheless, any representation like defined here should be reasonable to draw conclusions on the map. And now we consider two specific notions, topological transitivity and topological mixing. These are notions that are related to chaotic dynamics and essentially mean that the map mixes everything in the space. Every small set will grow by forward iterates to the entire space. And in a formal way, this is defined as follows. We say that a map is transitive if for every two open sets in the domain of the map, there exists an iterate such that the pre-image of one of them will eventually intersect the other. This means that the map sort of spreads out or smashes every open set all over the space. We can reformulate this into combinatorial setting by defining combinatorial transitivity. Well, we just copied the same definition, except now we have this multi-valued map, and U and V are vertices of the graph that represents this multi-valued map. So these are elements of the open cover, and we need to know that the set or the vertex, the element V, is in the pre-image of any other element of the cover after a sufficiently large number of iterates. Topological mixing is defined in such a way that whenever we have two sets, so this is something a little similar to transitivity, except in the topological transitivity, there exists an iterate that is high enough so that these neighborhoods intersect. In topological mixing, we need to know that there exists some number large enough so that all the iterates after this number get sort of mixed throughout the entire space. This is for all n greater than n. And if we copy the definition to the setting of this finite representation of the map, we get the notion of combinatorial mixing. We look at the pre-images by the combinatorial map. So these are pre-images of the single element, and these are finite collections of elements of the cover. And we need to know that we have this sort of inclusion of the pre-images. Now, what kind of algorithms can be used to prove these properties for some specific systems? We say that a finite directed graph that we use here, this is a pair of vertices and edges. Now we don't have weights anymore. And the graph associated with the combinatorial map is just a finite representation of this combinatorial map. The combinatorial map maps each element of the cover into a finite number of elements of the cover. And whenever this relation of mapping takes place, we just add edges to the graph. And now we use the notions of strong connectedness and aperiodicity of the graphs. We say, let me recall the definitions, a directed graph is strongly connected if for every pair of vertices there exists a path in the graph that goes from one vertex to the other. Also, we can define the period of a graph, and this is the greatest common divisor of the lengths of all the cycles in the graph. And we say that a graph is aperiodic if its period is just one. This essentially means that there are cycles of coprime periods, if you look at this in a different way. And now it turns out that the combinatorial transitivity and mixing correspond precisely to these features of the graphs. A combinatorial map is transitive if and only if the associated graph is strongly connected. And also a combinatorial map is mixing if and only if the associated graph is both strongly connected and aperiodic. And strong connectedness and aperiodicity, these are notions that can be verified for graphs in a reasonable time by effective algorithms. And in fact, there are linear time algorithms for checking these two properties. There is Tajan's algorithm, for example, that is based on DFS, depth first search, that can be used to compute the strongly connected components in linear time. I like the Tajan's algorithm because it doesn't require computation of the transposition of the graph. This is the same directed graph, except we take the edges in the opposite direction. From the theoretical point of view, computing the transpose of the graph is not really a big problem. It can be done in linear time. However, if the graphs that we use are large and they barely fit into memory, creating another graph of the same size is essentially requiring double the memory that we are already almost out of. So Tajan's algorithm is an efficient and an effective way of computing strongly connected components of a graph. Graph period can also be computed in an effective way using DFS, and it runs in linear time. It's maybe a little less standard algorithm, but for example, you can find one on Wikipedia. And since we couldn't find proof of this algorithm, we actually proved this in our paper. And my co-author, Stefano Uzzato, who works in ergodic theory of dynamical systems, was really impressed with the ingenuity of DFS. That first search was such a discovery for him that he insisted that we describe this algorithm in our paper. And we did it. And the paper was published in a very good journal, Foundations of Computational Mathematics. And then it includes the description of DFS and also the algorithm for checking aperiodicity of the graph. And in fact, we applied these algorithms to prove that the Henon map with the classical parameters is mixing and transitive. And from the practical point of view, which means that at all resolutions coarser than some specific very small resolution. In this paper, we introduced the notion of what it means that one cover is coarser or finer than the other one, and also what it means that some property of a map is satisfied at all resolutions coarser than some specific number. I'm not going to get into details, it would take too much time, but what is important here, if we prove this property for one specific combinatorial map that corresponds to one specific cover with very small sets, then we can use this entire theory to state that whatever coarser resolution you look at this map at, it will still have the same properties. So from practical point of view, this map will be chaotic. And this would be a very nice example if we can prove this kind of property for some models in epidemiology or biology or physics. Then we take the resolution that corresponds to the finest precision of measuring devices or the accuracy of the mathematical model, and then automatically we have this property proved for the entire biological or physical system. So this is sort of a picture, and the cover that we computed, we constructed this cover as a cover of the chaotic attractor that was built by, from squares. These squares overlap with each other a little bit. That is required by our covering because we take open sets. So they need to overlap a little bit. And this has a couple of thousands of boxes. We use these algorithms, we got the proof. Now, the third topic is a big project about developing sort of a computer assistant that would take a dynamical system, and then it would automatically decompose the system into interesting subsets and will show us the results. I'm not going to explain the entire project. Let me just show a few highlights and, of course, the graph algorithms. So we could have a dynamical system given, for example, by some ordinary differential equation. And what we're interested in is the recurrent subsets. So these are subsets, some trajectories whose points return to themselves or to their close vicinity. For example, if there is a fixed point, this is automatically a recurrent subset of the system or of the phase space because its image is itself. If we have a periodic orbit, like here, there is a periodic trajectory shown in red, then a point here after certain time comes back to its very close vicinity. So there is some recurrency, some recurrent behavior. There could be an entire disk of periodic solutions, and there's also some recurrent behavior observed here. So what we are interested in is to identify all the recurrent subsets, stable or unstable, such as fixed points, periodic orbits, maybe some chaotic dynamics, and also connections between these sets, so that we know that if we start at some sets, we can probably leave it and go to another set, but there is no possible connection from this set to, for example, to this fixed point here. And this would model some, for example, some biological system. We would know what kind of states of the system can appear recurrently and what kind of transitions of the system could occur. Here, we decompose the phase space into a cubical grid. So we just take squares or rectangles, or in Rn, we take n-dimensional hypercubes. We look at the dynamics at some bounded area. So we have a finite number of boxes. And now we look at the images of these boxes. Each box is mapped to, for example, to this kind of a bent set of complicated structure. But if we have a formula for the map, then we can use interval arithmetic or some, here specifically, we used CAPD software. This is computer-assisted proofs in dynamics software to compute these rigorous bounds in an effective way. And then once we have a box in Rn that contains the real image of the map, we cover this box by those hypercubes, by those grid elements. And in this way, we define a discrete representation of the continuous map in such a way that the image, the real image of a box, must be contained in the collection of boxes to which this individual box is mapped. So this discrete representation is a finite structure. Here we have a finite number of boxes. Each of the boxes in the domain is mapped into a finite set of boxes in the codomain of the map. We need to have this property that the actual image is contained in the interior of what we use here in this finite mapping. And this map can also be represented by means of a directed graph. Here we have a mapping on the phase space, so the domain equals the codomain, and therefore each element of this grid is mapped to several elements of the same grid, and in this way we define the graph. The vertices are going to be grid elements, and the edges here are going to be the relation by the mapping. So whenever we have a directed edge from one box to when we have the directed edge in the graph from one vertex to another vertex, if and only if there is the mapping between these boxes in the real underlying map. And it turns out that this simple representation of the map can be combined with some efficient algorithms to find a rigorous outer bound for all the recurrent dynamics in the system. And here we have sort of duality between graphs that represent the dynamics and the actual dynamics on the phase space. If we look at strongly connected components of the directed graph, then we get all the recurrent behavior, but you remember, if there is sort of an isolated vertex in the graph that is not on any loop in the directed graph, then we also treat it as a strongly connected component. It's just a trivial strongly connected component. But from the dynamical point of view, we want to see recurrence. So we need to have a mapping between the box and itself. That's why we only looked at strongly connected path components. And a strongly connected path component of a graph is just like a strongly connected component, except we assume that there is a non-trivial path. We need to have at least one edge to count this as a path from the element to itself. This could be a self-loop, it's not a problem. But this needs to correspond to something in the dynamics. Here we again use Tarjan's algorithm, which gives linear complexity of finding these connected components. And let's see the notions in dynamical systems which correspond to these strongly connected path components. Now, if we look at images of points and we allow ourselves to make a small error at each step, then what we get is called an epsilon chain. This is a sequence such that the image of ith point from the next one is at the distance of at most epsilon. And then a chain recurrent part of the dynamics is the collection of all these points such that the point can be connected to itself with an epsilon chain. So this is just like a path, a non-trivial path in the graph. If we take epsilon, where it is the size of the grid element, the size of this hypercube, then we can sort of prove a statement that every epsilon chain corresponds to a path in the graph, a loop in the graph, or a closed path that starts from a box and ends at the box itself. Nevertheless, the picture of the graph could look like this. In this graph, I marked in different colors the strongly connected path components that were found. And then we have some connections between these strongly connected path components. And these are not connections in loops. These are like in a gradient flow where everything flows from some higher altitude to lower altitude. And if we collapse each strongly connected path component to a single vertex, we can schematically depict this dynamics in a very simple way. We just have an acyclic graph. Each vertex corresponds to a recurrent set in the dynamical system. And then we have possible trajectories that correspond to paths in this scheme. And due to the definition of the representation of the map, we can prove, this is a real proof, that each strongly connected path component of the graph G is what we say an isolating neighborhood of the chain recurrent set of the map. Isolating neighborhood is a neighborhood, some vicinity, such that the chain recurrent set is contained in its interior. And this is a compact set. And between the components, the dynamics is gradient-like. This means that, for example, we have a computer-assisted proof that there is no trajectory in the system that comes from the green component back to the blue one, because we got an outer bound for all the possible trajectories. If we apply this to some specific system, we applied this to quite a few different systems, in fact, and our toy model was a Leslie population model that corresponds to in this case, a two-dimensional model. This is a 2-age model with discrete time. So this could be, for example, a population of trees in a forest, and we split the trees into two groups, young trees and old trees, and we look at there's some equation, there's some rule saying how the population the next during the next season depends on the population in the previous season. And for some parameters, we observed this kind of image in the phase space. So the phase space is the plane, and we found using the strongly connected path components, we found out that all the recurrent dynamics, in fact, is contained in just four sets. The black set is very small. It's somewhere here in the corner. There are two important sets, this red one and the green one, which are attractors. This means that if a trajectory starts in this set, it will not leave the set. And this is because if you look at the graph, there is no edge in the directed graph that points outside of the set. And the graph was a representation of some outer estimate for the map. So it's clear that we cannot leave these sets. This set is unstable. It's a period 3 orbit, and it shows that the population of the trees will vary in some cyclic manner. We don't have much insight into this set. It's just a large set. We can prove that if we start with the initial condition in this set, then after no matter how many iterates, we will not leave this set. And this is, by the way, an interesting observation from the biological point of view, because some applied scientists may say that the initial condition of the population doesn't matter. It will eventually stabilize at some attractor, at some attracting set, at some stable solution. And here we found two different stable solutions. And this is one, the green set. The trajectories will be wandering somewhere inside this set. And there's also another stable solution. This is a period 3 orbit that is found here in red. And this means that the state of the trees will oscillate, and these oscillations are a little dangerous because they come very close to zero. If we make a small error, the population of these trees could just die out. So this shows that we can find, using graph algorithms, some important conclusions for biological systems. In order to get some insight into those large recurrent sets, we recently introduced a new mechanism. We defined finite resolution recurrence. Namely, we don't just look at the recurrent components, we also measure the recurrence time. We check after how many iterates that we can get back to the box itself or to the vertex. This is sort of the minimal length of a non-trivial path in the directed graph from a vertex back to itself. And this finite resolution recurrence can also be computed in a relatively efficient way. We use shortest paths. We find shortest paths between all pairs of vertices within this strongly connected path component. And then we check for paths that leave a vertex u, go to v, and then come back from v to u, back to u. This can be computed using Floyd-Warshall algorithm. The complexity is like cubical. Since the image of each box is usually small, just a couple of boxes, not more than 10 or 20 boxes. And a more efficient algorithm is Johnson's algorithm, where we use n times Dijkstra algorithm with the Fibonacci heap, and then we get the algorithm of sort of quadratic complexity. So this is essentially, excuse me, this is quadratic complexity, a little worse because we have still this logarithm, and we run this algorithm n times. So we have essentially the number of vertices times the number of edges plus the number of vertices log v. So it is like n squared log n. And we did this computation. Oh, okay, I put this bound here. We did this computation for some sets in the Leslie model at some low resolution, and already looking at the finite resolution recurrence reveals the interior structure of the set. And here we draw a histogram of the recurrence times, how many times each of the recurrence time appeared in this model. For example, recurrence time 2 appeared only a few times, recurrence time 3 appeared almost 1,000 times, so almost 1,000 boxes were found with the recurrence time equal 3. We applied the same mechanism to the Henon map. So there's the Henon map again. You remember there's chaotic dynamics there. And in fact, the histogram looks like a normal distribution because there is this sort of topological mixing here, and recurrence times can be arbitrary without any specific rule. So if we look at finite resolution, we found recurrence times between 1 and 15, and in the middle there were the most points. So using these histograms for the recurrence times, we were able to use machine learning for heuristic classification of dynamics. And we did this in a model of a neuron with my co-authors at Gdańsk Tech. Let me just highlight 3 other applications where we used this algorithmic method for classification of global dynamics. We applied this to a population biology where we observed some interesting effects. This is collaboration with Eduardo Liz from Spain, from the University of Vigo. I also applied this in some theoretical physics paper with Benjamin Carreras, Irena Lerena from Barcelona, and some other people from Madrid. To get some interesting results, we found this limit cycle using this topological approach. And also, I tried applying this model, this algorithmic method in epidemiology to analyze a 4-dimensional model of infectious disease. And this is a joint work with some people from Hungary. That's all I wanted to say. Thank you for your attention.
Thanks a lot for your very nice and interesting talk. I don't know, Julian, if we have any questions on Facebook or on YouTube.
Let me check. We have a 10-second delay, so let's.
Okay, or maybe there is a question now. If anyone has any question?
There are no questions on YouTube.
Well, I assume everything was so clear. There's no need to ask anything.
We have one comment from Vinisha. It was a very nice, interesting talk here on Zoom.
Thank you.
I have one question. Have you applied or tried to apply some of these methods to the n-body problem, or the n-vortex problems?
No, I didn't apply to the n-body problem. There is a problem because I'm not sure if that system is dissipative. So we will have the images of the map, the images of individual boxes might be quite large, and then it will be difficult to find those attractors or to split the dynamics into recurrent part and non-recurrent part. In fact, everything on the entire phase space might turn out to be recurrent. So we don't get much information in terms of this kind of splitting. But what one could do is to still analyze the finite resolution recurrence to see the recurrence times in different regions of the phase space.
Thank you.
Okay, so maybe it's time to say thank you.
So thanks again, Paweł. Thank you a lot that you could find the time for us.
And we will continue on a few moments.
Okay.
For your attention and bye.